Okay, let's unpack this. Have you ever just felt, well, buried under too much information? Like, the sheer volume just makes it impossible to grasp what really matters or, how
So,
things connect.
oh, absolutely. It's a constant struggle, isn't it? We're basically swimming in data
Hmm.
and finding a way to organize it, understand its meaning quickly, and actually trust the systems built on it.
Yeah.
Well, that feels more important than ever.
Absolutely. We need structures that don't just store information, but really help us navigate it, clarify the relationships, make sense of complexity on the fly.
Exactly. We need better architectures
Mm.
for knowledge itself, really.
And that brings us to something truly fascinating. From the source material, you shared this technical paper, the Metamorphosis, and some related documents.
Right.
These sources introduce a pretty radical concept they call the Fractal Identity Map.
Or FAM for short.
Yeah, MEIM. Imagine a completely new way to structure just vast amounts of data. Designed from the ground up, the idea is to make complexity clear, understandable, inherently explainable.
That's the promise. That's the promise of the FEM, yeah, as described in these documents.
So our mission in this deep dive is basically to unpack this. We're going to explore what the FEM is at its core, dive into how the sources say it works under the hood, the clever mechanics,
Hmm.
and then look at why they believe it could be a genuine game changer for, well, everything from managing data chaos and building trustworthy AI
Which is huge.
to potentially even revolutionizing how we interact with computers using our minds. Seriously.
It's a concept that definitely touches on some of the biggest challenges in tech today. It really does.
It is. Let's jump right in then. At its heart, what exactly is this fractal identity map?
Okay, so the paper defines FEM as a multidimensional hierarchical system,
Hmm.
specifically designed for organizing representations of identity within data.
Okay, identity representations. What does that actually mean in this context? Like, what kind of identity?
Think of identity here pretty broadly. Any distinct entity or item could be a user, a device, a specific piece of data, a concept, an event, whatever. Instead of just having, raw data points floating around, the FIM organizes unique representations of these things. The identity map part is literally mapping these representations into a structured matrix or like a space.
So it's a map of the unique things and how they relate to each other.
Precisely. And while the sources do draw analogies from the brain, how the brain seems to organize information spatially, topologically,
Oh, I saw that.
this is fundamentally a computer science concept. It's an architecture for software and hardware, not biology.
Got it. Computer science. Now, the fractal part, we hear that word, think of, I don't know, snowflakes or coastlines. How does that apply here?
It refers to a structural property. The way the FIM is organized actually repeats itself at different scales. So if you could sort of zoom in on any part of the map,
Mm-hmm.
the organizational pattern and the rules governing it look structurally just like the whole map, only smaller.
Interesting. So the pattern of organization is self-similar everywhere, big or small scales.
Yes, that consistency is really key to its design. And crucially, this map isn't static. That's something the sources really emphasize its dynamic nature.
Okay, so it changes over time. It's not fixed.
It adapts
Yeah.
dynamically
Hmm.
based on how the semantic weights are distributed in the data.
Semantic weight. Okay, what's
Yeah.
that?
Well,
Sounds important.
it is. Think of it as like a numerical value indicating significance
Hmm.
or relevance, maybe frequency, important, basically how much something matters in context.
Okay.
As the data changes or maybe as the system learns, these weights shift. And the FIM can actually reorganize itself to reflect those updated relationships and priorities.
Okay, so it's a dynamic, self-organizing map
Yeah.
of identities based on their importance and relationships in the data. Did I get that right?
Exactly. You nailed it.
All right. Let's get into the mechanics then. How does the system actually work under the hood?
Okay, so it's built on this hierarchical prefix structure across multiple dimensions or axes. Imagine like a multi-dimensional address system. Each dimension can represent a different facet or context. Maybe one axis is subject, another is context, maybe time, source reliability, things like that.
Like coordinates, but the coordinates themselves actually carry meaning.
Precisely. And this is where meaning starts getting baked right into the location itself.
Oh.
Now, within this hierarchy, the elements branching off a parent node, think of them as children.
Uh-huh.
They aren't just listed randomly or alphabetically. That's not how it works.
Okay, how are they ordered then?
They're ordered by their descending connection weight from that parent. The sources call this Shortlex ordering. Basically, the children that are most important or most frequently connected to the parent appear first in that list.
Huh.
They essentially get a shorter or like more primary path in that specific branch sequence.
Oh, okay. Like organizing your desk, not alphabetically, but putting the things you use most often right at the front. Easy to grab.
Exactly that principle. But applied hierarchically and multidimensionally, this weight-driven ordering, Shortlex, is applied consistently across all the axes. And this structure, it leads to a really powerful mechanism they call meaning propagation.
Meaning propagation. What's that about?
It means children nodes automatically inherit the semantic context and attributes of their ancestor prefixes, the ones higher up the hierarchy.
Ah.
So if a high-level prefix on one axis denotes, say, highly secure data, everything nested beneath it automatically carries that attribute. You don't have to tag it again.
Wow, that saves a massive amount of redundant labeling then. The structure itself provides the context.
It does, exactly. And the deeper you go into the hierarchy, adding more prefixes to an address, the more specific you get. This is what they call precision reinforcement.
Right.
You're layering more specific meaning without losing the general context from the higher level prefixes.
Like adding a street number and apartment number to a city and state address. More
Ah,
detail, same foundation.
perfect analogy, yes. The system also uses something called an aggregator component, or sometimes they call it a metavector.
An aggregator or metavector. What's that do?
Well, it basically collects and combines all the identity-related data for a specific node. So it's prefixes across all dimensions, its weights, its attributes,
All the relevant info for that point.
right, into a unified representation, the metavector. Think of it as kind of a unique summary fingerprint for that point in the map. It helps encapsulate the aggregated information and, importantly, provides stability to that node's representation.
Okay. Stability. Got it. Now, the paper mentions some math. There was an E and a CDM. Without getting totally lost in the equations, what's the key takeaway for us there?
Sure, yeah, let's simplify. Think of E as basically the address length or the specificity level for any given data point's location in the map.
How deep it is in the hierarchy.
Sort of, yeah. The deeper you go into the hierarchy across dimensions, the larger E gets. And the paper shows that asking the system about a specific point, like why is this piece of data here, or what does this represent, takes a predictable amount of time. And it's proportionate only to the length of its address, E.
So it's efficient at a local level?
Very efficient locally, yes.
Oh, E.
Time complexity.
Okay, so E is about the efficiency of working at a specific location.
Right. And that CTN formula, that represents a potentially massive efficiency gain when you're searching or filtering across the entire map.
Across the whole thing, how does that work?
It works because of that weight-driven multidimensional prefix structure we talked about. The system can use what the sources call skip logic.
Skip logic.
Yeah. If you're looking for data related to, say, pharmaceuticals on one axis and clinical trials on another, you can immediately bypass vast sections of the map that represent totally irrelevant stuff like aerospace or geology or whatever.
Skip over the irrelevant branches entirely.
Exactly. You don't even look down them. So if at each level of the hierarchy, across n dimensions, you only need to look down, say, C relevant paths out of a total of T possibilities.
Okay.
You've reduced the search space dramatically, and that reduction, it scales exponentially, roughly by that factor, CT, raised to the power of n. If C is much smaller than T and n is large, that is an enormous gain.
Wow. Oh, okay, that's not just faster. That's exponentially faster search.
Yes, it allows you to navigate these massive data sets with incredible efficiency, focusing attention only where it's actually needed.
Okay, so building on those mechanics, what are the really big advantages the sources highlight about this architecture? One that jumps out immediately is interpretability and explainability. This feels, well, huge right now, especially with AI.
It really is. I mean, the paper positions this as a core fundamental feature. The coordinate itself, the prefix address, is the explanation.
Yeah, the explanation.
They call it self-leaning, which is maybe a bit of jargon, but it just means the location provides its own lineage and context just by being where it is in the map.
The structure is the explanation. The map is the model. That's a powerful idea.
Isn't it? It means you don't necessarily need a separate process or some complex analysis afterwards to understand why something is classified a certain way or how it relates to other things. Its position on the map tells you the story.
Right.
And like we said, the cost to get this explanation is efficient, just proportional to E, the address length. This directly addresses that whole black box problem we see in so many current systems.
That's incredibly valuable, seriously. What about overall efficiency beyond just the explanation part? Like, searching and processing data.
Yeah, that's where the skip logic really shines, right? Enabled by that hierarchical prefix structure, you can just prune away huge swaths of the data space that aren't relevant to your query or whatever process you're running.
And that leads back to the exponential reduction we talked about.
Yes, that CTN factor again. The sources even use this vivid phrase, faster than wind Cartesian lift.
Faster than wind. What does that even mean? Sounds cool, though.
It's a bit poetic maybe, but it captures how applying simple local rules, these fast operations, bounded by OE, at each node across the multidimensional hierarchy can generate exponentially powerful global results.
Ah, okay.
You could potentially identify and just discard up to CN irrelevant items with only linear OE work needed to navigate the paths that actually matter. The structure itself guides you.
So it prunes the irrelevant branches.
And reduces entropy, exactly. The structure focuses attention.
So the intelligence is kind of baked into the structure itself, amplifying simple actions.
That's the concept, yeah. The map design makes searching and processing incredibly efficient just by focusing your attention precisely where it needs to be.
Okay, efficiency is one huge thing. What about managing change? Data is constantly evolving, right? Does the system get confused, or does meaning just kind of drift around vaguely?
That's another key advantage they highlight, resistance to semantic drift. The system is designed to handle change robustly. It uses a threshold mechanism. So unlike, say, continuous vector embeddings.
The classic drifting embedding problem, yeah.
Exactly.
Yeah.
Where meaning can subtly shift over time in ways that are really hard to track or understand. Here, identity is anchored to these discrete prefix paths.
Okay.
Things only change position or get reclassified when the aggregated semantic weight, the overall significance and connections, shifts enough to cross a predefined threshold.
So like a statistical significance level, p.05 or something?
It could be implemented, something like that, yeah. The point is, it takes a meaningful change in the underlying data relationships to actually trigger a reclassification event. This prevents that sort of fuzzy, continuous, potentially meaningless drift.
So reclassification is a distinct, traceable event, not just fuzziness.
Yes, you can point to it and say, okay, this item moved because its connections changed substantially enough to warrant a new classification and therefore a new JOST. That metavector we talked about helps provide stability too.
Like the fingerprint.
Yeah, the inputs or outputs related to that node have to change significantly past that threshold to trigger a move. And it adds what they call additive precision, meaning deeper labels add specificity without overriding the higher context, unless that threshold is crossed.
That transparency about when and why things change seems like a huge deal. Now, how does this whole structure fit with modern computing? Hardware, parallelism, processing speed.
Right. Well, the sources say the prefix structure is inherently well-suited for parallel processing and even specialized hardware.
How so? What makes it good for that?
Different regions of the map, which are defined by different prefixes or combinations of prefixes, they can be processed independently with minimal interference between them. So you can assign different branches or like submatrices to different processor cores or different compute nodes, easily distribute the work.
So you can just throw more processors at it and it scales well.
Precisely. And that relatively low OE cost for work at each node. That supports what's called linear weak scaling. Basically, as you add more processors, the system can handle proportionally larger problems effectively.
Makes sense.
And the structure is also apparently amenable to mapping directly onto hardware like FPGAs or ASICs.
Custom chips designed specifically for this.
Yes. The sources mention concepts like a semantic address bus. Imagine a hardware bus where the location data, the prefix, travels with the data itself.
Okay.
So the prefix bits on the bus can directly direct the data and inform downstream logic about what the data actually represents. This enables hardware-based filtering or gating based purely on the semantic context encoded in the address.
Wow.
You could even build pipelines that process data differently based on its prefix. They mention applying wavelet transforms selectively based on scale prefixes encoded in the address.
That's directly leveraging the structure and hardware for speed and smarter processing.
It is. And different regions of the map could even reside on different hardware modules, allowing for parallel reads, writes, updates. Plus, the symmetrical design, where the same rules apply across all dimensions, means no single axis is likely to become a bottleneck for parallel operations.
Okay, let's talk applications then.
Yeah?
Where could this FIM actually make a difference? The sources use the 7 Whys framework, which felt pretty relevant to Well, anyone trying to navigate complexity today.
Right. Why should you, the listener, care about this? First off, just general data organization. It offers a way to organize huge data sets, making complexity feel manageable, clearer.
Yeah.
In our world of just constant information overload, the sources argue this isn't just about storage anymore. It's about survival and efficiency, navigating the chaos quickly.
Cutting through the noise effectively,
Yeah.
getting to the signal.
Exactly. Then there's AI and machine learning, big area. The FIM could potentially act as a structured, understandable long-term memory for an AI.
Right, the memory aspect.
And as we've discussed, the interpretability is baked right in, which is maybe the biggest need in AI right now.
It really feels like it. Interpretable AI.
And the sources take this even further. They strongly position IRAM as a way to address the whole black box trap and the broader challenge of AI alignment.
AI alignment, yeah. That's the big, scary, hard problem.
Right. But the idea here is that it's structural explainability. Remember, the map is the model, giving you OE. Explainability makes an AI's internal workings visible, transparent. You could potentially encode values, constraints, context directly into the structure itself.
So it helps address how we specify what we actually want an AI to value or prioritize by building it into the architecture.
Yes, potentially embedding it into the organizing principle. Plus, its resistance to semantic drift provides stability, which is also crucial for alignment. The sources really see this architectural approach as offering a tangible path through what seems like an intractable AI alignment problem.
A way out of the woods.
Kind of, helping combat that feeling of learned helplessness around AI safety, maybe restoring some agency and trust.
Wow. And for you listening, if you're in a business context, this translates pretty directly, doesn't it, to de-risking AI investments, maybe achieving true strategic partnership with AI systems because you can understand them?
And building stakeholder trust. Absolutely. By making AI decisions transparent, it's AI that can potentially explain why it's doing something, not just what it's doing.
That's the dream.
It also enables things like modular AI training and inference, anchoring operations efficiently to that E-value, and scaling throughput based on those semantic partitions using the CTN advantage.
Okay, now, here's where it gets particularly interesting, maybe even a bit sci-fi. Brain-computer interfaces, BCI. The sources propose mapping neural signals or maybe sensory inputs directly to these FIM prefix addresses.
Yeah, treating the location of neural activity or sensory input in the brain almost like a thimble to be mapped to a corresponding address in the FIM.
And the core problem this is trying to solve is the traditional byte rate limitation in BCI, right? BCI systems struggle with bandwidth today.
They often do, yeah.
Yeah.
They struggle to transmit complex, nuanced meaning efficiently. They can get raw data across maybe, but translating that into rich symbolic communication is hard because of bandwidth limits. So instead of trying to push huge amounts of raw neural data bits, which are high volume but maybe low density in terms of immediate symbolic meaning,
You could use the FUM structure to encode complex meaning into a deeper, more specific prefix address.
precisely. You scale the meaning conveyed by the length and specificity of the prefix address rather than just trying to pump more raw bits per second.
Huh.
A short, broad prefix might represent a general feeling or category. A long, deep prefix could encode a highly specific memory or concept or intention. It uses the combinatorial power of these prefixes to create an exponentially expanding semantic vocabulary.
That's brilliant. It leverages the structure to pack meaning efficiently. And you mentioned reverse lookup earlier. That means you could potentially trace a BCI signal represented by its FEM prefix back to its source, back to the neural activity or cognitive context.
That's the idea. The sources describe this as potentially creating a symbolic sensory spatial language, using the FEM as the dictionary and the grammar for that language.
That really does feel like a potential breakthrough for BCI, if it works. Beyond the semantic address splits we talked about, were there other specific hardware ideas mentioned?
Yeah, they mentioned things like highly efficient storage methods, using techniques that interleave the bits of the multidimensional coordinates in a way that reflects the semantic structure, making retrieval faster. The whole design really seems aimed at being hardware ready from the start.
Okay, so how does this FEM concept stack up against other ways we organize data? You know, traditional databases, knowledge graphs, maybe even the vector databases that are popular now.
Right. Well, the paper acknowledges it's combining features seen elsewhere. It mentions hierarchy like you see in tries. Spatial locality ideas may be borrowed from quad trees or space-filling curves. And the semantic richness you might find in knowledge graphs. It definitely integrates concepts.
But it argues the synergy, the combination is unique.
Yes, that's the claim. They highlight the key distinctions. It's fundamentally weight-driven in its structure and adaptation. which is different. It's multidimensional with truly symmetrical semantic axes. It's mapping semantic space, not just geometric points. It provides that built-in interpretability via location by design. It has that thresholded resistance to continuous fuzzy drift, and it's explicitly engineered for parallelization with those predictable OE performance bounds.
So it's the specific combination of these features and the properties that emerge from that combination, especially the inherent explainability and the drift resistance that the sources claim, make it novel.
It's presented less as just an iterative improvement and more like a different architectural philosophy for organizing information, one that leverages structure itself to provide meaning and efficiency. And when you compare it to purely geometric methods like Hilbert curves or Z-order curves, which linearize multidimensional data for indexing.
Right, they help find things nearby in space, but they don't know what those things are.
Exactly. They lack the semantic context. Hilbert or Z-order curves are mathematical constructs. They don't embed meaning in the bits of the index based on semantic relationships. FIM, on the other hand, uses these adaptive prefix codes that do reflect semantic structure, creating what you call a semantic filling curve.
A semantic filling curve. I like that.
And the sources really present FIM as a practical, verifiable architecture with clear mechanics, contrasting it perhaps with more purely abstract or speculative theoretical models out there.
It's designed for transparent, repeatable reasoning. You can follow the logic.
That seems to be the goal, yes.
You mentioned it's dynamic, so how is this map actually built initially? And then how does it adapt as new data comes in or relationships change?
The sources mention a couple of ways it can be constructed or updated. You could, for instance, generate it through graph traversal, analyzing relationships in existing data to build the initial hierarchy and weights.
Okay, learn from existing data.
Another really fascinating idea they propose is mapping signals directly onto the structure, like maybe neural backprop signals from training a neural network could directly shape the map, allowing the data processing itself to form the organization. It can be built recursively or updated incrementally over time.
So the data can literally help build its own map. That's neat.
Yeah, and once it's built, it adapts. Like we said, smaller changes in those parent-child connection weights. They trigger local reordering based on that Shortlex rule.
Just shuffling the kids around.
Pretty much, yeah. Children shuffle positions slightly within their branch to reflect their new relative importance. Local adjustments. But bigger shifts, the ones that cross that predefined significance threshold, those trigger discrete reclassification. The data item actually gets a new prefix address, reflecting its new semantic significance in the map.
A clear, defined event, not just gradual blur.
Right. It's a clear event, which helps maintain the map's meaningful organization as data evolves.
And adding totally new data points, how does that work?
It supports adaptive insertion. New data can apparently be placed into the correct spot in the hierarchy based on its connection weights relative to the existing nodes around it, fitting right into the Shortlex order. And this can happen incrementally, maybe even in real time, without needing to rebuild the entire map from scratch.
Which is absolutely essential for any system dealing with live, constantly changing data streams.
Absolutely. Critical.
Okay, so bringing this all together. The fractal identity map as described in the Metamorphosis and these related sources, it really seems like a potentially profound shift in how we might think about structuring information.
It really does feel that way. By embedding identity, meaning, and context directly into the location of data within this adaptive, weight-driven, multi-dimensional structure, it creates systems that are, well, inherently interpretable. Location is meaning.
Yeah.
They seem to offer incredible efficiency through that exponential skip logic. They're designed to be resistant to ambiguous semantic drift via clear thresholds. And they're architected for parallel computing right from the ground up.
And we saw how this architecture holds real potential to reshape fields like AI, offering that tangible path to explainability and alignment,
Huge.
revolutionize how we manage complex data, make sense of the chaos, and maybe even break fundamental limitations in brain-computer interfaces by scaling meaning itself, not just bits.
It's definitely a concept that resonates deeply, I think, with anyone who believes technology should amplify human understanding and align with our values. It offers a potential concrete tool for navigating the ever-increasing complexity we all face.
Okay, so here's the provocative thought the sources kind of left me with, maybe for you listening to. This FIM architecture suggests that complex meaning can emerge directly from how information is structured and spatially organized. Much like how the brain itself appears to organize information topologically, spatially.
that connection, or at least the analogy between this engineered structure and biological systems, is fascinating, isn't it?
It really is. So given that, maybe consider how you organize your own information, your own understanding of the world. Could thinking about your knowledge, your ideas, even your memories as a kind of dynamic, weight-sorted, multidimensional, self-similar map, could that fundamentally change how you approach learning, connecting ideas, and just making sense of things?
Mhm. It definitely makes you wonder about the very nature of knowledge itself and how deeply structure enables understanding. Something to chew on.